Turing faced a problem that no one could solve. It wasn't just a mathematical puzzle or some technical challenge. It was the fundamental question that would define the 20th century. What, exactly, can a machine do? And more disturbing still, where does the machine end and the mind begin? In the 1930s, while Europe descended into darkness, Turing was at Cambridge, surrounded by some of the greatest mathematicians on the planet, and all of them were lost. The German mathematician David Hilbert had launched a challenge decades earlier that seemed simple on the surface, but that revealed an intellectual abyss. Is there a universal method that can decide whether any mathematical statement is true or false? This question, known as the Entscheidungsproblem, or problem of decision, was not merely academic, it was existential. If such a method existed, it would mean that mathematics was complete, that human logic could capture all truth. If it did not exist, it would mean there were fundamental limits to what the human mind could know. Turing, a young Englishman in his early 20s, decided to attack this problem in a way no one had attempted before. Instead of working with abstract symbols and formal proofs, he imagined a machine, not a real machine made of metal and gears, but a theoretical machine, a mental device that operated with simple rules. This machine would have an infinite tape divided into squares, each containing a symbol. The machine would have a read head that could read the symbol, write a new symbol, move left or right, and change internal state. All of this based on a finite set of instructions. What Turing did was revolutionary because he transformed Hilbert's question into something concrete. If this theoretical machine could not solve a problem, then no machine, no algorithm, no systematic method could ever solve it. And he proved that there are problems this machine cannot solve. The halting problem is the classic example. There is no algorithm that can determine for any program and any input whether that program will eventually halt or run forever. This discovery was devastating and liberating at the same time. Devastating because it showed there were absolute limits to what could be calculated. Liberating because it defined precisely where those limits were. But here is what most people do not understand about Turing and about computation. You probably think you know what a computer is. You use one every day. You carry one in your pocket. You talk to one in your home. But you do not really know what a computer is. Not in the sense that Turing understood it. For you, a computer is a device that does things fast, that processes information, that executes programs. All true, but superficial. For Turing, a computer was something far more fundamental. It was the formalization of logical thought itself. It was the answer to the question, what does it mean to calculate? You think intelligence is something mysterious, something machines cannot replicate. You think there is something special, something ineffable, in human thought that makes it different from an algorithm. But Turing questioned this. He asked, if a machine can do exactly what you do, step by step, following rules, then what is the difference? And if there is no observable difference, then what is the foundation for saying a machine does not think? This question is not merely technical, it is philosophical, it is personal, because it touches something that defines us as human, our capacity to think, to reason, to understand. And Turing suggested that perhaps this capacity is not as special as we believe. Perhaps it is just a very complex algorithm. Perhaps the mind is a very sophisticated Turing machine. This idea disturbed people then. It disturbs people now. Because if it is true, then you are not so different from a computer. Your thoughts, your emotions, your decisions, all of this could, in principle, be simulated by a machine. You could be deceived by an algorithm and never know. In fact, you have probably already been deceived by algorithms without realizing it. Every recommendation you receive, every search result, every advertisement that appears for you is the result of algorithms that learn to predict what you want, what you will click, what you will buy. These algorithms do not understand you in the human sense, but they can simulate understanding well enough to influence your decisions. So Turing's question is not merely historical. It is urgent. It is about you, right now, in this moment. The story of Turing is the story of a man who saw beyond the limits of his time. Born in 1912 in London, Turing grew up in an era when mathematics was in crisis. The foundations that mathematicians believed were solid were crumbling. Kurt Gödel had proven in 1931 that any consistent mathematical system is incomplete. There are true statements that cannot be proven within the system. This was a shock. It meant that mathematics, the most rigorous discipline, or the most logical, had fundamental limitations. There was no way to escape. There was no way around it. There were truths that simply could not be reached by formal logic. Turing was studying at Cambridge when these ideas were still hot, still causing shock waves through the mathematical community. He attended lectures, read Gödel's work, absorbed the intellectual crisis of the moment. And in 1936, at the age of 23, he published a paper that would change everything. The paper was titled On Computable Numbers, with an application to the Entscheidungsproblem. It was dense, technical, difficult to read, but it contained an idea so powerful that it would reshape the entire 20th century. Turing had solved Hilbert's problem. He had proven that there is no universal method, no algorithm, that can decide the truth of all mathematical statements. But more importantly, he had done something else. He had created a precise definition of what it means to compute. He had drawn a line in the sand and said, this is what machines can do, and this is what they cannot. The implications were staggering. It meant that there were problems that were fundamentally unsolvable, not because we had not found the solution yet, but because no solution could exist. It meant that the human mind, for all its power, had limits that were absolute and unchangeable. It meant that the dream of a complete, perfect mathematics was impossible. Gödel had shown that mathematics was incomplete. Turing showed why, because computation itself has limits. But Turing did not stop there. He did not publish his paper and retreat into pure theory. He was living in a world at war. Nazi Germany was conquering Europe. Britain was fighting for survival. And Turing, with his brilliant mind and his understanding of machines and logic, was recruited to work on a problem that was not theoretical at all. It was desperately practical. The Germans had a machine called the Enigma. It was an encryption device, a mechanical cipher that scrambled messages into seemingly unbreakable code. Every day, German military commanders sent thousands of messages encrypted with Enigma. And every day, the Allies tried to break those codes. The Enigma machine had a keyboard like a typewriter. You typed a message, and the machine scrambled it using a series of rotating wheels. Each wheel had 26 positions, one for each letter of the alphabet. The wheels rotated after each letter was typed, changing the encryption pattern. There were 3 wheels in the standard Enigma, which meant there were 26 times, 26 possible starting positions. That is 17,576 combinations. But the Germans could add more wheels, and they could change the starting positions every day. This meant that the number of possible configurations was astronomical. It was estimated that there were more than 150 million possible settings. To break the code by brute force, trying every combination, would take longer than the war itself. But Turing understood something that others did not. He understood that the Enigma machine, for all its complexity, was still a machine. It followed rules. It was deterministic. And if it followed rules, then those rules could be exploited. Turing and his team at Bletchley Park, a secret facility in the English countryside, built a machine to break the Enigma. They called it the bomb. It was an electromechanical device that could test thousands of possible Enigma configurations per second. The bomb did not try every combination. Instead, it used logical deduction to eliminate impossible configurations. It used the structure of the Enigma machine itself as a weapon against it. The bomb worked. It broke the Enigma code, and this had consequences that were almost impossible to overstate. Historians estimate that breaking the Enigma code shortened the Second World War by several years. It saved millions of lives. It prevented the Nazis from winning the Battle of the Atlantic. It allowed the Allies to anticipate German military movements. All of this because Turing understood that a machine could be used to break another machine. That logic could be weaponized. That computation was not just an abstract mathematical concept, but a tool with real power in the real world. So let me ask you something. Turing had everything to stop. The world around him was collapsing. He was working in secret, under conditions of extreme stress, knowing that the work he was doing could determine the fate of nations. He could have walked away. He could have said that the theoretical problems of mathematics were more important than the practical problems of war. He could have chosen comfort over contribution, but he did not. He kept working. He kept thinking. He kept pushing the boundaries of what was possible. And when the war ended, when the Enigma was broken, when the Allies had won, Turing did not become a celebrated hero. He could not. The work at Bletchley Park was classified. It remained secret for decades. Turing could not tell anyone what he had done. He could not claim credit. He could not bask in the glory of having helped save millions of lives. Instead, he returned to pure mathematics and theoretical computer science. He continued to ask the questions that obsessed him. What is computation? What can machines do? What are the limits of the calculable? And in 1950, he published another paper that would prove even more influential than his first. It was titled Computing Machinery and Intelligence. In this paper, Turing asked a question that seems simple, but is profoundly unsettling. Can machines think? He did not try to answer the question directly. Instead, he proposed a test. He called it the imitation game. The test works like this. You have a human judge in one room. In another room, there is a human and a machine. The judge can ask questions to both the human and the machine, but the judge does not know which is which. The judge's job is to determine which one is the machine. If the judge cannot tell the difference, if the machine can convince the judge that it is human, then the machine has passed the test. And if a machine can pass this test, Turing argued, then it is reasonable to say that the machine thinks. This was radical. It was not asking whether the machine has consciousness or subjective experience. It was not asking whether the machine has a soul or some ineffable quality that makes it alive. It was asking a much simpler question. Can the machine behave in a way that is indistinguishable from human behavior? And if so, what grounds do we have for denying that it thinks? The philosophical implications were staggering. It meant that thinking was not something special or mysterious. It meant that thinking was something that could be simulated, replicated, mechanized. It meant that the boundary between human and machine was not as clear as we thought. It meant that you could be fooled by a machine and never know. It meant that intelligence was not a property of the mind, but a property of behavior, and behavior could be programmed. Turing's insight was this. The question, can machines think, was not a question about the internal nature of machines or minds. It is a question about what we can observe. If we cannot observe a difference, then there is no difference that matters. This is a profoundly pragmatic philosophy. It does not care about the metaphysical nature of consciousness. It cares about what we can measure, what we can test, what we can verify. And this philosophy has proven to be extraordinarily powerful. It has shaped the entire field of artificial intelligence. It has influenced how we think about computers, about algorithms, about the nature of intelligence itself. Every chatbot you talk to, every recommendation algorithm that predicts what you want to watch, every language model that can write essays and poetry, all of these are, in some sense, attempts to pass the Turing test. They are attempts to behave in a way that is indistinguishable from human intelligence. And many of them are succeeding. You have probably had conversations with machines that seemed intelligent, that seemed to understand you, that seemed to have something like consciousness or personality. But they do not. They are following algorithms. They are executing programs. They are doing exactly what Turing predicted. They are imitating human behavior so well that we cannot tell the difference. And this raises a question that Turing left unanswered. If a machine can imitate human intelligence perfectly, if it can pass the Turing test completely, if it can fool everyone, then what is the difference between imitation and reality? What is the difference between a machine that thinks and a machine that merely appears to think? Turing did not answer this question. He left it hanging like a philosophical sword of Damocles suspended over our heads, and we are still grappling with it today. The implications of Turing's work extend far beyond philosophy. They touch on the most urgent technological and social questions of our time. Consider artificial intelligence. Modern AI systems, particularly large language models, are built on principles that Turing would have recognized immediately. They are machines that process information according to fixed rules. They take input, transform it through layers of computation, and produce output. They do not understand in the way humans understand. They do not have consciousness or subjective experience. But they can simulate understanding. They can predict what you want to read, what you want to buy, what you want to believe. They can generate text that sounds human. They can write essays, compose poetry, answer questions, engage in conversation, and they are getting better at it every day. The implications are profound. If machines can simulate intelligence, then intelligence is not special. It is not the exclusive property of biological brains. It is a pattern that can be replicated in silicon and software. This means that the future of intelligence might not be biological at all. It might be digital. It might be distributed across networks of computers. It might be something entirely new, something that we do not yet have words for. But there is another implication that is even more disturbing. If machines can simulate human intelligence, then they can also simulate human irrationality, human bias, human prejudice. They can learn to discriminate, to manipulate, to deceive. They can be weaponized. They can be used to spread misinformation, to manipulate elections, to control populations. The same technology that can help us can also harm us. The same algorithms that can recommend good books can also recommend conspiracy theories. The same machines that can write poetry can also write propaganda. Turing understood this. He understood that computation was not neutral. It was a tool, and like all tools, it could be used for good or ill. He understood that the power to compute was the power to shape reality, and he understood that this power needed to be handled with care, with wisdom, with responsibility. But he also understood something else. He understood that the limits of computation were the limits of what could be known. There are problems that no algorithm can solve. There are questions that no machine can answer. There are truths that no computation can reach. This is what the halting problem tells us. This is what Gödel's incompleteness theorem tells us. There are limits, and those limits are absolute. They are not limits that we will overcome with better technology or faster computers. They are fundamental limits woven into the fabric of logic itself. This is both humbling and liberating. It is humbling because it tells us that we as humans are also limited. Our minds are also machines, in a sense. We also have limits to what we can know and understand. But it is liberating because it tells us that there are things that machines will never be able to do. There are aspects of human experience that cannot be computed. There are forms of understanding that transcend algorithm. There is something irreducibly human that no machine can replicate. What that something is, Turing left for us to discover. The life of Alan Turing was a tragedy. He was a man of extraordinary brilliance, a man who changed the world, a man whose ideas shaped the 20th century and continue to shape the 21st. But he was also a man who was persecuted, who was hunted, who was destroyed by a society that could not tolerate his difference. Turing was homosexual at a time when homosexuality was illegal in Britain. In 1952, he was arrested and prosecuted. Rather than face imprisonment, he accepted chemical castration. He was forced to take hormones that destroyed his body and his mind. He became depressed, isolated, broken. In 1954, at the age of 41, he died. The official cause was cyanide poisoning. It was ruled a suicide, though some have questioned this conclusion. What is certain is that Turing died at the height of his intellectual powers, at a time when he had so much more to contribute, at a time when the world needed him most. His death was a tragedy, not just for him, but for all of us. We lost a mind that might have solved problems we are still struggling with today. We lost a voice that might have guided us through the ethical minefield of artificial intelligence. We lost a man who understood, perhaps better than anyone, the power and the limits of computation. But his ideas live on. The Turing machine is still the foundation of computer science. The Turing test is still the standard by which we measure machine intelligence. The questions he asked are still the questions we are asking. What can machines do? What are the limits of computation? Can machines think? What does it mean to be human? These are not just academic questions. They are questions that will determine the future of our species. They are questions that Turing left for us to answer. And as we build more powerful machines, as we create more sophisticated algorithms, as we push the boundaries of what is computationally possible, we would do well to remember the man who first drew those boundaries. We would do well to remember that computation has limits. We would do well to remember that there are things that machines cannot do, things that only humans can do. And we would do well to remember that the most important questions are not the ones that machines can answer, but the ones that only humans can ask. Turing asked those questions. He asked them with courage, with brilliance, with a clarity of thought that few have ever achieved, and he paid a terrible price for asking them. But he asked them anyway. And that is what makes him not just a great scientist, but a great human being. Note: this script combines educational information with narrative entertainment elements to create an engaging presentation of Alan Turing's life, work, and philosophical contributions. While the historical facts are accurate, the narrative structure and some dialogue elements are dramatized for storytelling purposes.